and welcome to College Algebra. Today we'll be discussing section 1.7, where we'll be discussing linear inequalities and absolute value inequalities. All right, so before we begin, we need to discuss interval notation. And interval notation, there are basically two kinds of interval notations. We have open interval, where in notation form, we write it as in interval notation form, we write it as AB. If we write AB with a parenthesis around this, what this means, if we write this as a set builder notation, what this means is that there exists an x, there exists a number between A and B, and that number, so that means that number is greater than A, and that number is less than B. So we write this in set notation as S. X is said that A is less than X, and X is less than B. So X can be any number between A and B. And the closed interval AB is defined as in a set builder notation. We write this as X is said that A is less than or equal to X, and X is less than or equal to B. Now, so when you have a square parenthesis, it is a closed interval, and when you have a round parenthesis, it is an open interval. And we can have an example where we have open on one side and closed on the other side. For example, infinite, for this infinite interval minus infinity to B, this means it's open at negative infinity and it's closed at B. So we write this as X. For any real number X, we say that X is less than or equal to B. Or we have another infinite interval A to infinity, and this is X is said that X is greater than A. Alright, so let's look at some examples where we make use of such interval notation. So example 1, let's look at that on the next page. So example 1, using interval notation. Alright, so if we have, let's say, a set that is closed at -2 but open at 5, in set notation we write this as x is said that -2 is less than or equal to x, and x is less than 5. We can plot this on the number line. I can plot this on the number line as 0, 1, 2, 3, 4, 5, 6. This is -1, -2, -3, -4, -5. And it's closed at 2. It's closed at -2, and it's open at 5. So we do this and we join with a straight line. So this is how we plot the number line for this set notation. So let's look at another one. So be another example where we have a set that is closed at 1 and also closed at 3.5. So in set notation, this is going to be x is set at 1, x is set at 1 is less than or equal to x, and x is less than or equal to 3.5. Okay. And the number line, on the number line, we plot this as this is 0, 1, 2, 3, 4, 5, and this is -1, -2, -3, -4, -4. All right, so let's display this on a number line as so it's closed at 1. It's also closed at 3.5, which is somewhere in the middle of 3 and 4. So this is how we display on the number line. Let's look at one more example on set notation, interval notation. So if we have minus infinity, I said that is open at both minus infinity and -1. In set notation, this is going to be, we can write this as x. We say that x is less than -1. And on the number line from 0, 1, 2, 3, this -1, -2, -3. So x is less than -1. So from -1, moving all the way in this direction. This will be how we show this on the number line. All right, so let's look at finding, um, let's look at finding intersections and unions. Sections and unions of two intervals. All right, so for example, let's use this example. So use graphs to find the sets so that is closed at 1 and 3, and the intersection of that and the set 2, 6, and so that is open at both 2 and 6. First of all, let's graph the first set 1, 3. Let's look at the graph of it. So this is 0, this is 1, this is 2, this is 3, and this is 4. This is minus 1, this is minus 2, this is minus 3. And the set is closed at both 1 and 3. So at 1 and 3, we draw a square bracket and we join them by a straight line. So this is how we graph the closed interval 1 and 3. Let's graph the let's graph the opening interval. Um, let's graph. First of all, let me change this 2, 6 to um, um, let me change. Okay, let me change this example. Let me change this example. Let me change this example. Okay, let me make 2. Okay, let's continue. Let's continue with this. So the graph of the opening interval 2, 6 would also be displayed as so this is 0, 1, 2, 3, 4, 5. This is 6. This is -1, -2, -3. And this set is open at 2 and 6. So 2 and 6. So we can join the 2 with a straight line. Okay, so now if you want to find the intersection of these two, we'll have to look for numbers. We have to look for numbers that lie that can be traced to the intersection of these two on the number line. And we see that the first one starts as 1 and ends at 3. The second one starts at 2. So we can see that we have a point starting at 2 and a point ending at 3 that will lie in between these two number lines. So we say that numbers in both, we look at numbers in both of these sets, we see that 1, 3 is in intersection with 2, 6. We see that it would include a set that is open at 2 and closed at 3. So we see that 2, 3 is in the middle of both, but at it's open at 2 and closed at 3, as you can see at the top. So this is how we find the intersection of two sets by first looking at their number line. All right, so let's look at solving linear equations in one variable. Let's begin with an example. So, example, solve and graph the solution set. Solution set on a number line. And our question is 2 minus 3x is less than or equal to 5. All right, so 2 minus 3x is less than or equal to 5. We can subtract 2 on both sides. So if we do that, we're going to have, so if we subtract 2 on this side, we subtract 2 on this side, so we would have minus 3x is less than or equal to 5 minus 2, which is 3. So we can divide both sides by negative 3. And when we divide by negative number, the inequality sign reverses to the opposite. So this becomes x is greater than or equal to 3 divided by negative 3, which is negative 1. All right. So now we can show this on the number line. In interval notation, we will write this as, so in interval notation, we will write as x is greater than or equal to negative 1. So we write this as negative 1. We write this as negative 1, comma, infinity. X is greater than or equal to negative 1. And in set builder notation, the solution set, we write it as x is said that x is greater than or equal to negative 1. And let's try to graph this on a number line. So this is 0, 1, 2, 3. This is minus 1, minus 2, minus 3. And so greater than or equal to negative 1 starts from here. It goes in this direction as such. So this is how we graph x is greater than or equal to negative 1. Let's look at another example. So this will be example 4. And we solve the inequality. Solve the inequality. 3 3x plus 1 is greater than 3x plus 2. All right, so here, let's first multiply through by 3 on the left-hand side. So 3 times x is 3x plus 3 times 1 is 3. And this is greater than 3x plus 2. So we have 3x on both sides. So 3x, we subtract 3x on both sides and it goes away. So we now have, we will have, if we subtract 3x on both sides, um, so we then have 3 is greater than 2. And this is a true statement. 3 is always greater than 2. So it means this inequality is true. This inequality is true for all values of x. For all values of x, this inequality is true. The inequality is true. True here. Is true for all values of x because this statement 3 is greater than 2 is true. And in interval notation, we can write this in interval notation as write it as minus infinity to positive infinity. So every number between minus infinity to positive, every real number between minus infinity to positive infinity. In such notation, we can write the solution set as x is said that x is a real number. X is said that x is a real number. So this is how we write a solution for this. Let's move on to compound inequality. Let's look at some examples that involve compound inequality. So let's use another example to explain. So example, solve and graph the solution set. So this is example 5. Solve and graph the solution. Solve and graph the solution set on a number line. 1 is less than or equal to 2x plus 3 is less than 11. All right, so for this problem, the goal is to isolate the x term, to make the x term to stand by itself. So the first thing is if we subtract 3 on both sides, so 1 minus 3 is less than or equal to 2x plus 3 minus 3, which is 0, is less than or equal to 11 minus 3. So 1 minus 3 is also negative 2, which is less than or equal to 2x, which is less than or equal to 11 minus 3, which is 8. Uh, which is 8. Which is 8. And so let's divide both sides by negative 2. So we divide both sides by negative 2. Divide by, no, we divide by 2 rather, not negative 2. Divide by 2. And so negative 2 divided by 2 is negative 1, which is less than or equal to x, which is less than or equal to 4. All right, so we can write the solution sets. We can write the solution set for this as solution set. We can write it as x is said that negative 1 is less than or equal to x, and x is less than or equal to x is really less than or equal to 4. So this is really less than. Let me change this. Let me change this. So this is really less than. Okay, and in interval notation, we'll write this as um, -1, comma, 4 open. All right, and we can graph this also on a number line as, so this is 0, 1, 2, 3, 4, 5. This is -1, -2, -3. So it's closed at -1 and open at 4. So we can join these two by a straight line. So this will be how we graph this example 5. So let's look at example 6. So example 6, we have -4 is less than or equal to 2/3 of x plus 2 is less than 6. Right, so let's subtract 2 on both sides. The goal again is to get the x term to be by itself. So if you subtract 2 on both sides, we have -4 minus 2 is less than or equal to 2/3 of x, which is less than 6 minus 2. So minus 2 is -6, so -6 is less than or equal to 2/3 x, which is less than 4. All right, now we can multiply through by the LCM. We can multiply every term by 3. So -6 times 3 is less than or equal to 2/3 x times 3 is less than 4 times 3. So -6 times 3 is -18. It's less than or equal to this 3 cancels out this 3. So less than or equal to 2x. So -18 is less than or equal to 2x, which is less than, which is less than, uh, which is less than, which is less than 4 times 3, which is 12. All right, so now we can divide 2 by 2 and divide every time by 2. So that gives us -9 is less than or equal to x, which is less than 6. All right, so we can write the solution set as x is set at -9 is less than or equal to x, and x is less than 6. In interval notation, we can write this as a set that is closed at 9 and open at 6. All right, so let's try to graph this on a number line. So this is 0, this is -2, -4, -6, -8, and 10. And this is 2, 4, 6, 8. All right, so 9 is between uh, -10 and -8, and it's closed at 9, so somewhere here, and it's open at 6. So we join these two with a straight line past this. So this should be how we graph this. All right, so now let's move on to solving absolute value inequality. Let's look at solving absolute value inequality. Solving absolute value inequality. So to begin solving absolute inequality, when we have uh, the solutions of a variable u of u, absolute value of u, if it's greater than uh, a number c, uh, the solutions of it are the numbers that satisfy u is greater than c, or u is less than negative c. And on the other hand, if absolute value of u is less than c, then the solution are the numbers that satisfy the numbers that satisfy minus x. If minus x is a number, minus x is less than u, and u is less than c. So let's pick an example. So this should be example 7. So example solve and graph on a number line. Eighteen is less than the absolute value of 6 minus 3x. All right. So first of all, let's write this as absolute value of 6 minus 3x is greater than 18. And from what we just wrote down before, this, if it's greater than, then the solutions are 6 minus 3x is greater than 18, or 6 minus 3x is less than negative 18. Okay, so here if we subtract 6 on both sides, we have 6 minus 3x is greater than 18 minus 6, or 6 minus 6 minus 3x is less than minus 18 minus 6. So minus 3x is greater than 12, or minus 3x is less than negative 24. All right, here we can divide 2 by negative 3, divide here by negative 3. And if we divide by a negative number, the inequality sign reverses. So this becomes x is greater than 12 divided by 3. 12 divided by negative 3, which is negative 4. Or divided also by negative 3, negative 3, or x is greater than, the sign reverses as we divide by negative 3, x is greater than 8. Negative 24 divided by negative 3 is 8. All right, so in the solution set is x is said that x is less than -4 or x is greater than 8. And in the interval notation, now x is less than -4 is minus infinity 4 union x is greater than 8 means 8 to infinity. And so we can also graph this on the number line. This is 0, 2, 4, 6, 8, and -2, -4, -6. And so x is uh, greater than x is, oh, sorry, so I should have flipped the sign here. After we divide by negative, the sign reverses to be less than, and when it is less than already, reverses to be greater than. Um, so x is less than -4 or x is greater than 8. So on the number line, x is less than -4. Starts from here, it goes in this direction. And x is greater than 8, starts from 8, and it goes into this direction. All right, so let's look at another example on compound inequalities. So that will be our last example, example 8. Okay, so example 8, we have 7 plus absolute value of 4 minus x divided by 4 is greater than or equal to 12. All right, so first of all, let's subtract 7 on both sides. So if we do that, then we have absolute value of 4 minus x divided by 4 is greater than or equal to 12 minus 7, which is 5. So we have absolute value of 4 minus x divided by 4 is greater than or equal to 5. All right, so then from here we can write this as 4 minus x divided by 4 is greater than or equal to, 8, or 4 minus x divided by 4 is less than or equal to -5. Oh, I don't know why I'm writing 8 here. It should be 5. All right, so from here we can subtract 4 on both sides, and that gives us minus x divided by 4 is greater than or equal to 5 minus 4. So minus x divided by 4 is greater than or equal to 1. And at this point, we can multiply 4 on both sides. So times 4 and times 4 here. So this 4 cancels out, divides this 4. So we have minus x is greater than or equal to 1 times 4, which is 4. Okay, so then from here, if we divide both sides by -1, then we have x, the sign reverses, so x is less than or equal to -4. And on this side, we do similar. We should subtract 4 on both sides. We have minus x divided by 4 is less than minus 5 minus 4. So this becomes minus x divided by 4 is less than equal to minus 9. And if we multiply both sides by 4, then we have this 4 divides this 4. We have minus x is less than or equal to minus 9 times 4, which is negative 36. And if we divide both sides by negative 1, then we have the sign reverses, so we have x is greater than or equal to positive 36. So it's negative 36 divided by negative 1 is positive 36. So in interval notation, we write this as x is less than or equal to negative 4, means minus infinity to negative 4, and union x is greater than or equal to 36. So 36 and positive infinity. All right. And there's right in interval notation, we say that in set notation, we write this as x is said that x is less than or equal to negative 4, or x is greater than or equal to 36. All right, so let's draw this on a number line. So on a number line, we will have, so on the number line, we're going to have, let's draw this on a number line. From 0, we have 10, 20, 30, 40, and here we have negative um, and negative 20. All right, so 4 is somewhere here between negative 10. Negative 4 is somewhere here between negative 0 and 10. And x is less than or equal to 4. X is less than or equal to 4. Is in this direction. X is less than or equal to 4 is in this direction. And x is greater than or equal to 36. It's also in this direction. All right, so this brings us to